Hi, everyone. Welcome to our second lecture bite of the week. This is week 8, protoplanetary disks. So last time we talked about how astronomers have been looking for patterns in the solar system planets for a very long time. And one of the most important patterns that they noticed was the idea that the planets in our solar system seem to be orbiting in flat, orderly way. So if you put all of the planets and draw circles around where they orbit, all of those circles seem like they roughly go in the same plane. So like you could almost fit them onto one piece of paper instead of having some planets that orbit in 3 dimensions and go around the sun like this and go in and out above and below the plane of Earth's orbit, which is technically possible, but which we don't see here. The other thing that was noticed is that all of the planets seem to orbit in the same direction, and that they also happen to orbit in the same direction that the sun spins. And the hypothesis that was made by people like Immanuel Kant and others is that this is because the planets formed from what we call a protoplanetary disk, a disk of gas and dust that formed right after the formation of the star, or as the star formed, and spiraled around in a flat disk-like shape and caused all of the planets to kind of conglomerate, accumulate from material within the disk. So let's talk a little bit about how this might have happened and what some of the current observations are in favor of the protoplanetary disk model. So I've showed this animation a few times already, but it's one of the most important concepts in all of astronomy, the formation of stars. So I'll show it again. So here we have a cloud of gas that started out relatively uniform, but quickly there were perturbations that ended up becoming more and more accentuated as the gravity, the self-gravity from all of this gas started to pull itself together. And as this happens, regions of this become dense enough and dense enough that they turn into protostars, or even start stars that end up getting hot enough in their cores to start fusing helium or hydrogen into helium. And you can see that these stars are being formed, and lots of them are doing it all at the same time, and they're getting ejected from this system. So let's look at another animation which shows a close-up view of what happens to some of these stars as they're forming and right after they're forming. So this is going to show in a series of different zoom-ins, and you'll see what I mean in a second, a bunch of different stars that are forming. So these yellow regions are bright, they're more dense, and as more dense regions come to be from the simulation, they'll start popping up here. And what you can see is that at first, a lot of these kind of just look like round globs, but eventually the gas distributions end up flattening out. So why is it that these gas distributions end up flattening out? The answer is that if everything were going around in random directions around a star, eventually the gas would crash into itself. If you have gas that's coming around this direction and other gas that's coming around this direction, those gas particles will collide and they'll eventually end up moving in the same direction because that's the path of least resistance. So this is what happens. And what that does is it forms a disk of gas that's all moving in the same direction, which of course matches our observations of the solar system because all of the planets and the sun itself seem to be moving in the same direction. And you can see that there's lots of interactions happening. There are many stars orbiting around each other in this. I'm going to zoom forward a little bit until we get some more action. Um, and you can see that as this is happening, you can start to get very beautiful patterns. You can start to see spirals as perturbations from other stars are starting to drive density waves in those disks. You can start to see disks flying by each other and getting tweaked and perturbed like that, and some of them even spewing off material as they're being tidally stretched. So the process of forming disks around stars that have just formed is actually very natural. As soon as your star gets to be massive enough that its gravity is dominant over everything around it, you have to have a disk. Otherwise, the leftover gas that's around there just doesn't have anywhere else to go. It has to start moving around all in the same direction as everything else. So these are some simulations, and they look pretty convincing, but what can we say about them with observations as well? So how would we go about testing this? One way to do it is to look at regions of the sky that look like they might be about to form new stars. So here's a beautiful mosaic of a star-forming region called the Taurus Molecular Cloud. This was taken by the European Space Agency's Herschel telescope, which observes in the infrared, or which observed in the infrared. It's no longer functioning anymore. And you can see that there are these beautiful filaments and these kind of long tube-like structures that look very similar to the structures that we saw in the simulation. So this looks like a good place where we might want to look. So let's start looking at particular stars or particular bright regions within this molecular cloud. So now I'm going to switch to an image from the Hubble Space Telescope of a handful of particularly interesting young stars. And the first one I want to focus on is this one down here, which is called V1213 Tauri, although astronomers usually shorten the Tauri to Tau. So now let's take a look even closer at V1213 Tau. So this is a really striking image. And the first thing you can see is that there is a flat pancake-like thing over here. There's some bars of stuff extending out this way. And then there's this cloud of diffuse material over here. So what's going on? This is actually the disk. This is the flat region of gas orbiting around a star. We can't actually see the star here because we're looking straight through all of the middle of the gas. This disk is perfectly lined up with our line of sight so that we have to look straight through the disk to actually see the star. And all of that dust and gas in the disk is blocking our view. This line of material coming out from the top and the bottom of the disk is called a jet. As material from the disk spirals inwards and moves towards the star, it eventually crashes into the star and is doing something we call accreting. So what happens is that strong magnetic fields are formed on the star as this process. The star is moving very rapidly. There's charge moving all around. That creates magnetic fields. And these magnetic fields are twisted in the direction of the star's spin. And what that does is it can actually accelerate material and get shot out the top and the bottom of the star. It gets shot out of the system, and it produces this jet of very fast-moving, energetic material that you can see flying off into space. When this material from this jet collides with other regions of gas, you can get a sort of diffuse glow as that jet interacts with them and heats them up. And this is what we call a Herbig-Haro object. So let's zoom in even further. As I said, where is the star? There should be a star here. It turns out we can't see it because we're being blocked by the gas and the dust from this disk. And the other question is, why does this disk look like a hamburger? Why does it have a bright spot up here, a bright spot down here, but a dark spot in the middle? Is it really a double-sided disk? And the answer is no. It's actually just one thick disk, but this region is so opaque, so totally blocking light that it looks dark to us. We can tell actually that this disk is really one thin piece of material, and we're just seeing the light peeking out the top and the bottom when we look in radio wavelengths. In the radio, the star is no longer bright, and we can actually see the emission from the dust, the warm dust emission. And this is what it looks like in the radio. You see that there's just essentially one thin contour of material, which then falls off as you go higher and lower on the disk. So the next object to take a look at in this image is called HL Tauri, or HL Tau. So up here you can see it, and it's basically very bright. So this one, we actually can see the star in the optical, and the star is so bright that it essentially blinds us. So we can't get too much out of this image from Hubble in optical wavelengths. So let's just look straight at the infrared. And when you do that, you see something really amazing. So again, the star is not very bright in the radio wavelengths. So you don't see a star in the center here. But what you do see is you see the emission from the dust. And you can see this beautiful flat disk, Frisbee disk-like thing. And what's really striking about this image are these rings and these gaps. These are places where there's more dust and less dust, respectively. So the dark areas have less dust, the bright areas have more dust. What could be causing these rings? Here's another example of an image of a star, a young star that just formed, taken in radio wavelengths. These are all images coming from the ALMA Observatory in Chile, by the way. In this case, you can actually see a spiral arm, just like the ones we saw in the simulations. So what's causing these spirals? What's causing the structure, the rings, the gaps we see in the disks? So it's actually pretty ubiquitous. When we look at a bunch of disks, almost all of them seem to have some sort of ring-like structure or spiral-like structure. And the idea is that perhaps these gaps and these spirals are caused by planets that are forming. Here's a simulation of a disk that's been tweaked to look very much like HL tau over here. And what they're essentially trying to do is they're trying to make a map of a disk that looks like this, where you have rings of brighter, more dust, and then little gaps where there's very little dust. And they do a pretty good job. You can see that if you put a planet here, this bright region here that's kind of showing up in the gas. So this is the gas distribution where there is gas, and this is the dust distribution where there's a lot of dust. And you can see that in the gas, you get this kind of spiral arm shape, and in the dust, you get these rings due to this planet and its gravitational interaction. So perhaps the best interpretation of these gaps is that these are due to the results of newly formed planets that are still in the disk, that are still being built. This is very much an active area of research. And one of the things that we're trying to figure out is, do we really believe that all of these rings, these spirals, and these gaps are caused by planets? Or could they be caused by other things? And if they are caused by planets, what kind of planets could be doing this? So here's an example of a kind of a gallery of images of some of the different types of protoplanetary disks that you can see. So here's a really beautiful spiral arm protoplanetary disk. Here's HL tau, which I just showed you from the ALMA observatory in the radio. Here's some others with some interesting structures here and there. So like you can see this little gap right here, perhaps. There's an asymmetry here. There's less dust over here than there is over here, apparently. And then there's this big hole in the center. And kind of on and on, you see these different structures. So one of the areas that researchers are currently working on is trying to predict where planets might be. So if I plop down a planet in my simulation, where can I put a planet so that it gives a structure that looks very much like these real observations? So the prediction here from a fellow named Robin Dong, who's a professor in British Columbia in Canada, is that you need a big planet here, about 10 times the mass of Jupiter, to cause this big spiral. But for HL tau, you need a couple of smaller planets that are less massive than Jupiter. And if you put them in the right places, you can make your simulations look very much like what we see in our observations.